We are moving to even a more advanced topic. So I hope you also pay attention, and if you have any question, let me know. Yeah. Using scanf and sprintf? No, it doesn't work like this. Maybe what you need to specify if you want to do exactly this is don't pass the full string. Basically scanf and sprintf operates the same way exactly as you deal with the screen. So it scans the screen from the beginning, looking for a certain character that matches, right? So it will do the same thing. If you want to read a certain character from this one, you either don't use sprintf or scanf, which is actually the easier solution. Or if you specifically want to use this, is you pass the input string such that it starts with the letter that you're looking for. Right? So you do it yourself, you scan it, you stop, you basically define another array. That starts with the letter that you want to actually take and put in the other variable, right? But by this, sprintf and scanf has actually no useful use case in the example that you mentioned. Okay. Okay. So pointers. Okay. So this topic is confusing for so many, but actually it's an easy one if you pay attention to the way it works or understand what happens behind the scene. Don't just focus on programming. So what happens behind the scene, we mentioned before, is basically each variable has a place in memory, and this place has a specific address, right? You remember we discussed this? So when you define any variable, what you do, assume I define int x. What the program is going to do is go to the memory. This is int, so it's 4 bytes. So because the memory is byte addressable, so it takes 4 memory locations, 0, 1, 2, 3, 4, and then this will hold the value of x, starting from address 0. This is the address here, right? Sometimes you need the value of x, but some other times you need the address of x. Can you give me an example that we covered so far that we need the address of x? Yep. But if you read from the user, you just take the value, right? You don't take the address, yeah. If you pass this variable to a function that you want to change, right? We said you cannot have multiple return values from a function. What if I want to change 2 things in a function? We said a solution for this is to pass these 2 parameters to the function as an input, but pass them by reference. And we mentioned that passing by reference is sending the address of the variable rather than sending the value, right? And we had an example of a and b and x and y. Good? So this is one example of you need the address of x to pass it to a function that will later modify this memory location. Good? Okay. This is what is stated here. And to deal with this, we had the AND operator. I told you before, this is the way you pass things by reference, and basically it means the address of this variable. So one example here is, this is my main. I define a variable n equal to the value of 6. Then I do print 2 things. I print the memory location for this n is at address. I'll tell you what is this right now. But here, and n is the address of n, not the value. So and n is not 6, right? And n is the place in memory that this 6 is stored. So it's a memory address. The value of n is this thing. And we had this before, and basically you print n. So it will be an integer value, which is 6. So we know that the second line will give us 6. But the first line will give us where the 6 is located in the memory. So if you try this out, you will see something like this. So the memory location for n is at address this. 0x, you know what is this? You know hexadecimal values, right? Digital logic design course. Do you guys know what is binary and hexadecimal or no? Yeah. So this is just a value, right? A number, but it's represented in hexadecimal representation. And this is how we deal with addresses in computers. like you have a memory that is 4 gigabytes. It starts from address 0 up to 4 gigabytes is actually 2 to the power 22. You go to the address 2 to the power 22, but because this is a very big number, we represent this as hexadecimal. Right? So 0x here means hexadecimal, and this is the value. Good. So what you see here is the address of n. How did I get that? You did this by using the AND operator, which gives you the address, but also you want to print this in a hexadecimal format, and this is the specifier of like %b. This is how you print a pointer to the screen in a hexadecimal representation. Right? Do you have any question here? So conceptually, a pointer is another variable that stores the address of the variable that you are talking about. So you have n and you have the address of n. These are two different things. N is the value itself, but the address of n is a pointer to the location of the memory where the value is stored. Okay. So because n is an integer, so it has 4 memory locations. Which one of this is the address of n? Is the starting address. Because I told you in the previous example here, it went away, but basically an integer is 4 bytes, and memory is, every location holds only 1 byte. So what is printed here is only the address of the first byte. And then the remaining ones are just +1. So this is the address that we have here. N starts from here, and then you put it here, you put it here, you put it here. Right? Good. So it makes sense that you cannot apply the address operator to a constant. The reason is, this is from the very, very first lecture. Why I cannot apply the address operator to a constant? Yeah? The constant is not even stored in memory. You don't have an address to that one. So what does it and mean? And deals with an address and a memory. Constant is just a constant. It's not stored in the memory, right? This is why you cannot use that or even that. Good. I already discussed this with you when we talked about arrays. I told you that the name of the array, if you define an array int a array, what does a represent? It represents a pointer to the first index or element in the array, right? So I told you arrays are contiguous places in memory that starts with a certain address, and then you keep increasing with this address, right? If it's an array of integers, then the first element is a certain address, and then +4, +4, +4, because each entry of integer takes 4 bytes, right? So if you define such array, and you guys, you have laptops, you can actually try these things while I'm talking. It's good to see things yourself. So basically the memory location for B0, which is the first element, is, and I'm here printing the address of the first element, the second element, third element. What you can see is a certain address, which is for B0. By the way, this doesn't have to be the same thing that you see. Can you imagine why? You may get a different number, even if you actually run the same application on your laptop. Why maybe you get here a different number? Yeah? Yeah, it will be allocated to whatever place you have empty in your memory. So when you run things are running in the background in your laptop. You have the operating system, other applications running. So when you run this specific one, it gets placed in a certain place in memory. What is this place? It depends on what is empty. Sometimes it's the beginning of this address, sometimes a completely different address, right? So it's okay to have different results here. But the thing that will be fixed is the difference between these two will be always 4. Why? Because we know that B0 or the array itself is integer. That means, and it's contiguous in memory. So whatever address you start with, this is +4, +4. And you can try this yourself. Is there any question?
If you got the address for just B without an index, would that give you anything? Would that mean?
If you?
So if B is an array and you didn't index a point.
B0, for example.
Yeah, if you just did B, 2 square brackets, would that give you anything?
Without the and thing?
Yeah, without anything between brackets.
No, right? You cannot, even this is not a valid syntax in C, right? Maybe you just write B, not B with brackets. And we will see this now. So B is just the name of the array, which I told you it's also a pointer to the first element. And we have an example on that. Thank you. Okay. So this was related to what you said, is actually the name of the array is a pointer to the first element. So if we try this, if this is what you were looking for, so here I try to bring two things. The address of the first element and the address somehow that is B. What is B is the name of the array. I told you that the name of the array is a pointer to the first element. You can verify whether what I said is correct or not by doing this. Okay, I'm telling you that the name is a pointer to the first element. So let's print the address of the first element and the value of this B. If they match, that means that's correct. B is actually a pointer to the first element. If they don't match, then what I'm saying is wrong, right? This makes sense? So if you print these two, you have to get exactly the same result. The reason is B, the array itself, is the address of the first element of the array. Good? We explained this when we discussed arrays in memories. Good? Okay. Is there any question? Good. So we also discussed this. We said, as a compiler, as a C compiler, how would I know if you define such an array and then you access element 2, B2, or B1, or B4, or B5? How would I know which memory location it is? Can someone explain to me? Come on, from the back. If I define an array B, and then I want to access B5, as a compiler, how would I interpret this B5? The same faces every time? Other people? Yeah? Yeah, first, B gives you the first element, right? And then you said 20 because I said the fifth element, which is, it's an integer, so it's 5 by 4. So it adds 20 to this address, right? So this is exactly, thank you. Please give me your name afterwards. Okay? So what your friend here is saying is basically I have B. B is a pointer to the first element. I want to access B5, which is here. 0, 1, 2, 0, 1, 2, 3, 4, 5. This is 5. How would I get this address? You already have this. You know each entry here is 4 bytes, so you multiply 4 by 5, which is your index, and then you go to this address. And I gave you an example about this before. Good? One problem is C, for the third time I mentioned this, has no boundary checking. What it means is if you actually try to access B minus 2 or B 200 or anything that is outside your boundary of the array, it will not complain. That doesn't mean your code is correct. It means actually it's very risky. Why it's very risky? Because now you are accessing a place in the memory using the same math that we have here, but it's not part of your array. So it can be part of anything else. It can be an address of another variable, or it can be an address to a variable in a completely different program. It can be anything. So your program can crash, other programs can crash. Your operating systems, hopefully not, because you are not within an authenticated region, but may crash, and actually this has a security implication. Some people use this to access certain memory addresses that has authentication bits for the operating system. So it has a security application here, but if you don't intend to harm your computer, then you shouldn't be doing this. You have to make sure that you are within the boundary of your defined array. Otherwise, you are accessing a base in the memory that you don't know what is it. If you read it, then that's okay. Maybe your program has a wrong value. But if you write into it, this is the risky thing. Right? All of this is here. How do we define a pointer? We have been talking about pointers a lot. How do we define a pointer? So the way you define the pointer is to use this asterisk character with the type. So int, this asterisk means you are defining a pointer to an integer variable. So what is in front of the pointer definition is not the type of the pointer. It's the type of the variable that the pointer is pointing to. And this is what confuses people. So if this is the type of the variable of the pointer that it's pointing to, then what is the type of the pointer? Do I need a type for the pointer? Yeah, but why? This is what I'm like. What is the logic behind it? Why a pointer is a type of itself? Can't a pointer be like double or character or string or int or anything? Yeah? Yeah, you cannot have a decimal address to a memory. You cannot have an address in a memory that is 1.5. And you cannot have address in the memory that is hello world, right? It cannot be a string or double or anything. It has to be actually an integer value, right? Right? So a pointer is a type that by nature holds only address, like value of addresses. And an address is actually a positive integer value. It cannot be negative. It cannot be a double. It cannot be string. Right? So a pointer is a type of its own. But what you write here is not the type of the pointer. The address can point to anything, right? It can point to any data type because you can place in the memory any data type. And this is what defines what the pointer is pointing to. If you have any question, let me know. If you are confused completely, also let me know. Okay. So we'll have some examples. So I guess if you are still not very sure, let's see. So here I'm defining an end pointer that I call end pointer. This is a pointer to an integer variable, right? So, and if you place the asterisk here or here, it doesn't really matter. It's exactly the same thing. This is a pointer to a character, right? So let's see if I have a pointer to an integer variable. This is the pointer itself. But remember, the pointer, which I called end pointer here, is also a variable, right? So it has a place in the memory, that it has an address to it, right? Do you see that? So let's look into the example. So here I define two things. An integer variable, this is very easy. A place in the memory has a value of 8 and it has this address. Good? We have seen this before. End pointer, this is the problematic thing. The only thing you need to understand is pointer is nothing other than a variable. So again, it's exactly the same thing as this one. It has a place in memory, it has a certain value, and it has an address, right? The only different thing about pointers is what is this value? It's also an address, right? So this one, if you assign the address of n to n pointer, it will basically take this address here, right? It will copy the address of n and put it in the value of n pointer. As you can see, this is a thing and this is a completely different thing. This is an address to a variable, but this is the address of the pointer itself. And this can mean that I can have a pointer to a pointer, right? This makes sense? Because a pointer is nothing other than a variable that has an address. This address I can point to by anything else, right? It's getting confusing more and more. Yeah? So let's see some more examples. So if you want to imagine this thing, as if I'm saying by assigning the address of n to n pointer, I'm saying the value here is actually pointing to this memory location, right? Good. So this is what we have done. Now I'm initializing, I'm changing the value of the n pointer to 20. And this in C has kind of complex name that is called indirection or dereferencing. And basically, it just changed the value. So how would I explain this? Okay. So now I have, this is my memory. I have n here. I have n pointer pointing to this one. Assume, forget about these things for now. Assume this address was 5. That means n pointer has a value of 5. Later, I change it 5, which this is, what is this line about? I change it 5 to 20. But Because I'm not changing n pointer itself, I'm changing this thing. You remember when we said this AND is your address operator? On the other hand, your asterisk is the value operator. What it means is when you use this asterisk in front of the pointer name, you are not referring to the pointer. You are referring to the value that the pointer is pointing to. What the hell? So you have x variable, you want to pass the address of x to a function, we use AND x. We said AND x will pass the address of x, right? When we come to pointers, asterisk does completely the opposite thing. Asterisk is used with a pointer, but not to access the pointer value, which is the address, to address the value of that pointer, which is here n. So when I say n pointer is 20, I'm not changing the address. I'm actually changing the value that this pointer is pointing to. If n was originally 8, I'm changing this to be 20. Make sense?
So basically, like, it places 5 with 20 or 8 with 20 in that same jar. Like, if we think of the address to be like a jar.
Yeah. If this memory location is a jar and the pointer is pointing to it, it replaces what is inside the jar. Yeah. Okay. Yeah.
So just to confirm, so this is not changing the memory address of AND, it's just changing the value.
Yeah.
How would you change the memory address?
How would you change the memory address? We will see how to assign. One example would be, maybe I'll ask the question in a different way. How would I change the value of a pointer? Right? So originally, this pointer had no value. But then I changed it by assigning it to an address. Right? So what is this address? Is basically making pointer pointing to a certain memory location. You cannot change the address of this variable because it's already assigned by the hardware. But what you can change is what n pointer is pointing to. For example, you can have another variable here that is m. You can assign n pointer to m instead of m. Okay? Okay. So here is another example of using pointers. Ask as many questions as you would like. Right? Because this is actually a complex topic. I don't mind spending even the next lecture on the same topic. Right? So if you have many, like whatever question you have, please ask. Yeah.
Can we change variables together by having their addresses equally? Sure. Can you change the address of a variable?
Yeah, this is exactly his question. You cannot do this. And the reason is they are already placed by the hardware. That's why it's important to understand what is the logic behind pointers. Right? Actually, even in C, you cannot assign a fixed address to a pointer. There are indirect ways of doing this. But you cannot say, I want my pointer to be 0x453. Right? And because this 453 may not be within the area that is allocated to your program. If you know what are the limits in the memory that is allocated to your program, you can do this. But maybe 0123 is in an operating system region. Right? It's like an advanced topic. Like to answer your question, no, you cannot change the address of a variable. Okay, so here is another example. Don't ask each other. I mean, you can ask each other after the lecture. That's okay. But I'm here to be beneficial to you. So maybe you just ask me. Yeah.
If you were to define A and B first, could you then assign the pointer to the address of B all in one line?
So you define A and B, and then you want to assign. Oh, so you say if I. That's an very interesting question. So what you are saying, if I define everything in one line, int A, B, and B pointer, for example, or maybe just what I have done here, but I want to assign B pointer on the same line as A and B? What you're saying?
Well, no, assign A and B first, and then the next line do int star B pointer equals at B.
Yeah, initializing the pointer when defining it, right? You can do this. You can. Because, again, it's a variable. And we have rules in C to initialize a variable, which you can do on the same line that you define it. So you can do this. And this is very similar to do this. We are initializing my pointer, but just to a null. Right? You can replace the null with and B after you define B. Well, so the example here, I defined an integer pointer. Initially it's null, so it has no it has no value, it's just 0. And then I define two variables a and b, 25. I make the pointer is pointing to the b location by assigning it the address of b. And then later I'm saying a has the value of the variable that b pointer is pointing to. As you can see, this is completely equivalent to say what? A equal b, because b pointer is pointing to b. Later, I am dereferencing b pointer by just saying it's the value of b is 0. Right? So, in the first line, null means address of zeros. Yeah. It here, making it as a null. Here? First line, okay. Yeah, because this is a pointer, right? Okay. That's also important to mention. The asterisk has two uses. Defining a pointer and the dereferencing thing. When you define, so when it has a type in front of it, it's not dereferencing, it's defining a pointer. Right? So this is just telling, if we don't have this, that means b pointer is just an integer variable, right? It's what we had before. But by doing the asterisk here means this b pointer has to be a pointer to an integer, right? When dereferencing happens, when an asterisk means dereferencing, when you find it in an assignment expression, you assign something into it. Yeah. No, because we said asterisk here means the value that the pointer is pointing to. So remember when I said and means the address and asterisk means the value? This is how we should consider it. So asterisk pointer means the value that the pointer is pointing to, right? Which is b. That's an interesting thing. So null is not a valid memory location. Null is not a memory location. This is why it's safe to initialize it with null. Say it points to nothing now, just to be in the safe side. This is a good programming practice. If you define a pointer as null, you say I'm not pointing to anything, because if by mistake you change it like it's the value that is pointing to, you are safe. You are not changing any place in the memory. So it's a good practice when you define a pointer to initialize it with null. Yeah. It's not necessarily. This is what I'm saying. But it's good practice. Like, did you infer from what I said? It's like it's a must. It will not give you an error or something, right? But it's safe. It's safer to initialize it to null. And actually, some compilers would by default do this, even if you didn't initialize it. But what I'm saying is, like, to be completely safe across all platforms and compilers, just do it yourself. Thanks.
So if you like in A right now, we get a value of.
Yeah, I'll discuss this. I'll discuss this. Who stores the address of a pointer? Right now, we don't point into this by anything, but you can define another pointer that points into it, right? I don't know if this is clear, right? You can ask the same question before we cover pointers. Guys, I'm okay to answer any question, but I'm not okay that you keep talking, because... Okay, so this question is very important. It's saying what stores the value of, what stores the address of the pointer itself. If we didn't cover pointers, like if you come to me before this lecture, and you ask me what stores the address of the integer variables int x, we didn't use it, but the address is in the memory itself, right? But we didn't point into it. So, and pointer is just a normal variable that has an address. If you need to use it, you define another pointer that points into it. And we will have more examples later. Linked lists and these kind of things. But if you don't use it, then you don't need to store it anywhere. The memory already knows where pointer is located, right? So the hardware has this knowledge. What pointer does is not store the address. It just provides you an access to this address, right? You basically copy the address into a certain variable. So let's go through the example and make sure you understand what is going on. So I define a pointer, initialize it to null. This is why it has this value here. I define two variables, A and B. I initialize B to 25, but A has no value here. And then in the line 3, I assign the pointer to the address of B. So it takes this address. This is the address of B, right? And then in the 4th line, I say A has the value that the pointer is pointing to. What the compiler is doing is, and please focus on this. In line 4, what the compiler is going to do to execute this line, go to this pointer, take the address, go where in the memory this address is pointing to, takes 25, copy it to A. These are the 4 steps that will happen when you do dereferencing in C. Take the address of the pointer, go to the memory, copy the value that this address is pointing to, and place this in the variable that you are assigning the value to. So here, take this address, go to here, it's B, copy 25 into A. Good? And then finally, you say the value that the B pointer is pointing to should be 0. What will happen is you will copy this address, go to the memory, and replace it with 0. A will remain 25. Why? Because pointer is not pointing to A. Pointer is pointing only to B. And there was a question right here. I guess this answers the question. Do you have any question? Okay. So you can assign an address of a variable to a pointer. We have done this. You can assign a null to a pointer to point to nothing. We have done this. You can also assign a pointer to a pointer. And the reason is they have the same, but it has to be of the same type. So if it's a pointer to an integer, and then you have another pointer to an integer, you can assign pointer A to B, right? What will happen in this case? Both pointers will be pointing to the same memory location, right? So here, I say pointer 1 is null, pointer 2 is null, and then I define later, and I define another integer variable n. And then I assign the address of n to pointer 1. This will happen. Then later, I say pointer 2 is equal to pointer 1. So both will point to n, right? Clear? This makes sense? Do you have any question? Okay. So later, if I say pointer 2 equal, like the dereferencing thing, the value that the pointer 2 is pointing to should be 76, then n will be 76. Right? What if I do this later? Int m equal n pointer 1. What should be the value of m? 76, because pointer 1 has the same address as pointer 2. You change it this, so pointer 1 is pointing to 76. We'll take the value, place this in m. Right? Yeah.
What's the point of having two?
That's a good question. What is the point? So first of all, we are just discussing what can we do. We didn't say use case, right? But his question is, what is the point of having two pointers pointing to the same place? Good. Assume, and this is later in linked lists. But assume you don't know what is linked list, right? You have one memory location. And then you have one pointer pointing into it. You want to keep the address of this variable. But on the same time, you want to do a math operation on the pointer that it's pointing to. Then what you need to do, define another pointer to this variable, and then change the original pointer, right? So right now, it's not a valid use case. It does nothing because pointer 1 is not changing. But later in the program, if you change pointer 1, so last time we stopped here, we started discussing pointers, one of the most confusing topics in C. I hope last lecture at least introduced you to pointers and how to deal with them. Today we are going to continue the same topic. Again, if you have any question, please let me know, because this topic is important. It's actually very important even in general programming. It's important for whatever coming course, and the pointers concept is the same no matter what is the programming language you are using. For example, if you're going to program in the future using Java or something else, pointers are pointers. So the concepts are exactly the same. This is why it's very important. This is why I'm paying attention to what is happening behind the scene, what are the concepts behind what's going on, how the memory is structured, and why we need pointers, how they are used. And then the syntax is what is limited to C, but then it's very similar to other languages as well. Right? If you have any question, let me know. So today, we didn't discuss this last time, right? Or you don't remember? Did we discuss this? Swapping two variables, a function? Okay. So by the way, all the lectures are on Avenue. Since I guess the second week of the course, you guys requested that I put the lectures before. So since then, I have been doing this, if you don't know. So you already have these lectures so that you can take notes during the lecture. Okay, so what we want to do here. It's a very simple function, similar to what we were doing before. You want to swap two variables. The different thing here is, because you want to swap two input parameters, then the result is not just one output, right? So if I asked you to write a function that returns the like the maximum of two numbers or three numbers or n numbers, then the output is just one variable, right? If I asked you to sum two numbers or subtract two numbers or divide two numbers, the output is just one variable. Functions in C and in most programming languages have this limitation. You can return only one variable, right? In basic ways. Then here we want to swap two variables. That means my output should be two things, right? Because this is the result. How I do this? We discussed before the concept of passing something by reference, which means you don't pass the value of the variable itself, you pass the memory location of that variable, right? We already discussed this before. Today we are going to put everything together. Some things we covered in variables, some things we covered in functions, something we covered in arrays and pointers. So today's lecture is actually dependent on all the lectures we discussed so far. So if you missed one concept before, then it's the time to get it. And if you didn't imagine how things happen together, today we are integrating this together. So today is a very important lecture actually. Right? So we want to swap these two. That means we have to pass them by reference because you want to change both. Good? There is no other way to do this. Good. So, and this is the AND thing. You remember from last lecture we said AND is the address, right? So you are not passing A, you are passing the address of A to the swap. Or in other words, because we already started pointers last lecture, in other words, you are passing a pointer to this variable, not the variable itself. Right? And this is why swap doesn't return anything, because the result of swap will be reflected in the two input parameters. Right? What we do here is because you pass an address, you read this in a pointer. And this is the first time we see these two things. How to input a parameter to a function as a pointer. It's the first time we see it as this syntax, but we have seen passing an effective pointer to a function before. Does anyone know what is that for a bonus mark? So what I'm saying is, this is the first time we see something like this syntax. You are passing a pointer to a function. But before, we had a very similar, not very similar, it's the exact effect, but in a different syntax. Yeah? When you were passing arrays, because we said array, name is the pointer to the first element in that array, right? Effectively, it's a pointer, it's a memory address. And this is why, again, passing array to a function is going to change it, so it's by default a passing by reference. So why you can, the function, when it reads an array as an input, it has the ability to change it. Why? Because array is a pointer, effectively the name of the array is a pointer to the first element, and you are passing a pointer to a memory location. That means if you make any change in this memory location, it will reflect. It's not like passing a variable. Right? And this is the basic concept in pointers. You have to differentiate between the value of a variable and the memory address or the memory location of that variable. Right? Okay. So we define two pointers, the read addresses, so they have to take this. Why these are int pointers? Because the variables themselves are integers. That's why the pointer has to be a type of int, right? And then what you will do here is I define my temporary memory location, because you have to define a temp thing if you want to swap. You assign, what does this line do from last lecture? Yeah? Yeah, you assign the value that y pointer is pointing to the temp. What is this value? This is y pointer. It takes the address of P. That means this is effectively P. Right? Is that clear? So what I'm doing here is, this is dereferencing, pointer dereferencing. This is the term that is used in programming, but aside from the term, we said this and is an address, this asterisk is a value. If you see the asterisk in front of a pointer, not in the definition, but using it in the assignment, that means you are using the value that the pointer is pointing to. Good. So this is B, you put it in temp, and then you switch Y and X, or effectively A and B, and then you assign them. Basically, this is the basic swap, 3 lines that you have seen multiple times before. Is there any question here? No? Okay. So, if you want to see what's going on, assume A and B are 100 and 200. You define these two pointers. Right now, they are not pointing to anything. But once you call the function that goes to swap, this X pointer will take the address of A, this Y pointer will take the address of B. And then inside the swap function itself, you define the third memory location, which is N, 4 bytes. By doing this, temp is equal Y pointer, you go here, take the value that Y pointer is pointing to, 200, it goes to temp, and then third line, what you do is you take X pointer, which is A, go to B, and then you put A in your, you put temp in your A, right? This is a kind of tracing or simulation to what's going on. Good? Any question? Okay. So the thing that we want to do here is, I want to write a function taking the same concept even further. I want to write a function that takes 2 input parameters and returns to me the sum and the difference between these 2 variables. Now I want to return 2 things, which means what? I cannot use this. I cannot use the normal return process of a function to return both. You can only return one of them, right? But given now we know pointers, you don't even need the return, because what should I do here? Can someone imagine or say what would be the prototype of the function? It takes 2 input parameters and you want to return, or you want to find the sum and the diff yet. But I don't want to change X and Y. What I want to do is read X and Y and calculate their sum and difference. So if I only read X and Y, how would I reflect back? Think always in a function, think of what are your inputs, what are your outputs. It's like a black box, right? You read 2 things, which is X and Y, that's true. But you want to return completely two different things, which is the sum and the difference. What you are saying is, I can return the sum and the difference each in X and Y as well, right? This is what you are saying? Let's say I don't want to do this. Let's say I don't want to change the 2 input parameters. Yeah? Yeah, so pass to the function as well another 2 inputs. You call it sum and difference, and then use this to calculate whatever you want to calculate and keep X and Y the same, right? So the prototype would be explanation of what we have just said. And then the prototype, this is calling the function, so you have X and Y, and then these are the 2 variables that you want to change. Here, I'm passing X and Y by value. Why? Because I don't want to change X and Y. I'm just reading them. But I'm passing sum and diff by reference, because these are my results, right? And then let's just go here. So the prototype of the function itself would be a and b, normal variables, and then here 2 pointers to read the sum and def. These are effectively not inputs to the function. These are outputs, right? So maybe initially they don't even have a value in the main function or the caller. They will get their value after calling the function itself. Good? What I would do inside the function is I'm just going to assign the value of a plus b to the sum pointer dereferencing thing, which means the memory location that the sum pointer is pointing to is going to hold the sum of a and b. Similarly, the memory location of like the def pointer is pointing to is going to hold the difference, and then I'm done. Just 2 lines. Good? And because these are pointers, they are going to change, or the change will reflect on the main function as well. So when calling this, sum and def will actually have the sum and difference of these 2 numbers, right? So sum def in the main are variables. Sum pointer, def pointers are pointers pointing to these variables. So if here you are not actually changing the pointer itself, this is dereferencing again, so you are changing the variable that the pointer is pointing to. I feel like I'm repeating myself 1,000 times, but that's okay. If you get it, this is the important thing. So if you have any question, let me know. Yeah. Storing it as a pointer. Which ones you are referring to? These 2? Yeah. So these are pointers, right? Pointers, we use them as addresses to a memory location. But at the end, you want the result of this sum, and this is what is important to you, right? This is the logic that you want to implement. But you are not going to store the sum into the pointer, because the pointer is a memory location. You want to store the sum in a specific memory location, not a memory address, right? You get that? So without this dereferencing thing, without this asterisk, this is not going to work, right? So the trick of a pointer is you use the address to change the memory location, not change the address itself. Because if you do this, then what is the difference between a pointer and a normal variable? It's nothing. Yeah. Good? Okay. So again, a simulation to what's going on. Some pointer, def pointer are pointing to 2 memory locations, and then a and b has certain values. You do the sum, and by doing this, you take the sum, put it in the sum, and then, so let me say step by step what happens behind the scene, at least for one time, for the sum, for example, right? So this line, what the compiler will do is, this is a pointer dereferencing. That means I should go to the sum pointer value, read the address, go to the memory location that the address is pointing to, and use this variable. What I'm going to use this variable in, assign the sum into the variable. So add these 2, 300, take the address, go to the memory location, put the 300 here. This is what compiler or the hardware at the end is going to do when you execute such a program. Good? Okay, the same thing for def pointer. Any question? Okay. So we continue discussing pointers, but by adding things together, pointers and arrays and dealing with functions. And at the end, if we have time, we'll discuss dynamic memory allocation in C. Let's see. Okay. So one thing we have been doing so far is using the pointer as an address to change a memory location. But we didn't do any math operations on the pointer itself, except for the array, because I explained to you, and this is one thing that we will revisit today, that array name is a pointer to the first element, and when you access an index or one entry in the array, like A5, for example, what the compiler is doing some math operation in the A. So it reads the address of the first entry, add, assume this is an integer array, each entry is 4 bytes, and you want to access A5, so the entry number 5, then what the hardware is doing is take 5, multiply it by 4, because each entry is 4 bytes, this is 20. You add 20 to the actual start address, and this is going to be your location to the entry number 5 in the array, right? So this is somehow a math operation on the A, which is the pointer to the first element. So today we are generalizing this, not just for arrays, for pointers. If you want to do some math operations on the pointer itself. Why I would like to do this? I already give you one example. Like, you know that array is contiguous in memory. If you have the pointer that is pointing to one element, you should do some math operation, addition or subtraction, to move throughout your array, right? So this is one example to do this. If you add something here, like b plus I, this is advancing the pointer by I entries. And one very important thing, this is basically the main difference between doing math operation on a pointer and in a normal variable. If b is a normal variable and I want to add I, and I assume I is an integer value of 5, what will happen? You take the value of b, you add 5 to it, and that's it. Right? Very basic. We have covered this in the first lecture. But if p is a pointer, it's completely different. Because if you read the address of p, you are not going to add 5 to this address. It means nothing. b is a pointer to a certain data type. Assume b is of integer type, right? That means each element that b is pointing to is 4 bytes. So if you say, I want to do b plus I, and the I is 5, logically, you don't want to add absolute 5 value to the pointer itself. You want to read the variable that is pointed to by like a part of 5 memory locations from the certain variable. What does that mean? Again, let's go to the array example. You want to visit A5, but A, the pointer that is pointing to the first address, is at A0 by default, right? If you say A plus 5, this should take you to the A5, not to the 5th byte after A, because the 5th byte after A is, can someone imagine where is the 5th byte after A? So let's say I have this array. So let's say I have this array, and this is 0, 1, 2, 3, 4, 5. I want to access this one. And I know that if this is array A holds the address of the first element, right? If I do A plus 5, what you expect logically is this should point to this entry, right? But if you add the absolute value of 5 to assume this A is just 0x0, is like first element is at address 0. If you take 0 and add absolute 5 to it, that means this is address 5, right? And this is int. Can someone tell me address 5, where exactly it points? Yeah? Yeah, it's actually not the beginning of the number 1. It's the second byte of the first of entry 1, right? Because entry 0 is from 0 to 3, because it's 4 bytes, 0, 1, 2, 3. Right? And then entry 1 is starting from byte 4, 5. So I'm going to point to the second byte of entry 1. This makes no sense. Right? So effectively what you want to do here is add 5 to not the pointer value itself, but to the segment that the pointer is pointing to. So if A is an array of integers or pointer of integer type, you want to increase the memory not by 5, by how much? 5 multiplied by 4, the size of the integer. Right? Makes sense? Because effectively this one is at address 20. Come on. Okay. Sometimes you shouldn't trust technology. Okay, this. Okay, this one is at address 20 because this is at 0, this starts at 4, 8, 12, 16, 20, because it's integers. What if array A is of type character? It's different because integers are 4 bytes, but characters are just 1 byte, right? So if A is array of characters, this is going to be address 0, 1, 2, 3, 4, 5. In this case, you don't multiply 5 by something. So to generalize this, what I should do is not use the absolute value that you want to add, but multiply it by the size of the type the pointer is pointing to. Make sense? We'll see some examples now. So this is a double array. I define a double pointer. To assign some value to the pointer, I can do this, right? What a pointer would be doing, it's going to point to A4, right? Because I take the address here. You can say a pointer plus 3. Which element this is going to point to? Can you see? A7, right? Right? Did you get that? So, what is going on here? This is dereferencing, but before you do the dereferencing, you do a math operation on the pointer, right? So we calculate it one by one. A pointer holds the address of A4. You add 3 to this. We said this calculates to A7 address, and then you do dereferencing. That means this is equivalent to say A7 equal 10, right? So here we combine math operations on pointers with dereferencing. So you can also subtract if you would like. This is going to point to element number 2, because originally we were at A4, this is going to be A2. And what you're doing here is assigning A2 equal 10. There is one risk or one dangerous thing about using pointers to do assignment to array elements. What is this one? What is the risk? Yeah? Can someone, yeah? Yeah, because again, C has no boundary checking. If you do this math operation, and here it seems very simple because you have a static value, 2. It's just an immediate value. But generally, 2 can be anything, can be another variable that you calculate from other things. This is a normal C expression. So this subtraction, you can subtract anything. And this variable can be calculated from another thing, so the program can be complex enough. You want to check that you are not indexing an element in the memory that you don't know what is it. So you have to stay within your array boundaries if we are discussing arrays. Okay? So one possible math operation is the pre-increment, right? So you pre-increment your pointer and then you assign it a value. So if a pointer here is pointing to 4, you pre-increment it to 5, then you go to element 5 and then assign 10, right? So far, these examples, we're doing math operations in pointers, but using immediate values. I said also this can be any other variable, but a pointer in C is nothing other than a variable. So can we do math operations using 2 different pointers? Can we subtract 2 pointers, add 2 pointers together? Right? Then yes, we can do this. So let's say I define 2 pointers, A and B. This is again an array. And then A pointer is pointing to element 8, which is this one, 18. B pointer is pointing to 3, which is 0, 1, 2, 3, 13. And then I do subtract both. But here what I'm subtracting is not the value. Can someone say what is the value of I? And this is for a bonus mark. Yeah. 5. The reason is 18 minus 13, right? Not true. This has no dereferencing. It doesn't have the asterisk thing. So you are using a pointer as the address, right? Then, yeah, which is it, okay. That's right. That's true. Well, I should add different numbers here, because in both cases it will be 5, but that's bad. Yeah, thank you. Yeah, that's true. So basically, A pointer minus B pointer will take the difference between the indices, the entries, right? Not the values in the entries, but here it happens to be the same, right? Good. So it's 8 minus 3, not 18 minus 13. This is a bad example. Okay. Okay. So one thing to learn is the difference or the addition would be an integer value. Again, I told you pointers are memory addresses at the end. Memory addresses are positive integer values because you don't have a negative address and you don't have a floating point address, right? It's an integer, like this makes sense. Memory is a physical thing, so you don't have a negative memory location, right? So the difference between them is an integer value. But this may confuse you that a pointer is also of an integer value, but that's not true. A pointer is a type of its own in C. It holds integer values, right? Because it doesn't take negative values or floating point values, but it has its own type, yeah.
Will the compiler throw an error, or like will it throw an error at runtime if it finds a negative pointer?
Yes, but it will do this, but if the expression, so if it's very clear, like you're saying, you're defining a pointer like this one and saying -2, it will complain, right? But if you are doing complex math operations, the compiler may not be able to detect this because the compiler has different levels, right? So first it does a syntax check, but it doesn't calculate so you need to know what are the values to know whether the result is a negative value or not. And you will not know the values until you execute it. So in some cases you will get an error if it's an immediate value that is clear to the compiler checker, or in some other cases you may need to execute and then it will give you a segmentation fault when executing because the expression wasn't clear at the beginning, and then when you executed, the hardware found itself that it has to go to a memory location that does not exist, and this is segmentation fault. Right? So it depends on the case. Right? Okay. So this is explaining what happens behind the scene to get the difference of 5, right? We calculated this 5 ourselves by saying, okay, this is at location 8, this is at location 3, I calculate the difference, right? But this is an integer array. Another thing would be like a double array or a character array, right? So difference in number of entries will be the same, but the actual number of bytes, the address itself will be different. What I mean by that? 5 entries in an integer, they will have a memory size of 5 multiplied by 4, 20 memory locations, right? But 5 entries in character have 5 memory locations because each one takes only 1 byte. It's 5 bytes, right? For double, if it's 32-bit, then the same as the integer. If it's 64-bit, then it actually holds 8 bytes. So you multiply 5 by 8, so it's 40 bytes, right? So size of is a function. We will see this function later, but what you need to know now is size of gives you the actual size of the type. So size of int gives you 4 bytes. Size of, we tried this when I asked you to try in your machines what is the size of an integer, what is the size of a floating point number. We tried this before, right? Okay. Here we have another example, and this is, assume this is my memory. So what I'm doing here is I'm defining an array of 5 elements, A, and then assigning a pointer B to the first element of that array, A. So now B is pointing to 10, right? The first element. And then in the line here, I'm printing the value of B. Can you imagine what is the result of this print? By now we should know this as our names, right? So we have so many examples. So what would be the result of this printing? Yeah? 10, right? So here I'm doing dereferencing. B is pointing to A. A is an array, which means the name holds the address of the first element. This should be 10. And then I'm increasing my pointer, B++. Now by doing this, B is going to point to 20. So if you print it, what you would expect from this line? Someone from the back? Yeah? The memory location or the address of 20, not 20 itself. The reason is I had the specifier as B and I'm not doing dereferencing. So I'm printing the address itself. And this is the trick here. Here we printed the value that B is pointing to, but here we are printing B itself, which should be the address of 20. And then I'm increasing by 2, going to 40, doing the same thing. So originally B is pointing here. B++ is going to point to A1, and when I print this one, it should give me this address, right? And then B+2 is here, which is 2 memory locations after the A1, which should be A3. So something you see from this memory here is each element has 4 bytes, right? Because these are integers. So you print the first line gives you 10, the second line gives you B after you increment it by 1, which is 0x22AA04, and then you increase B+2, this is jumping here to A3, which is 0C. Any question? No? Okay, so we already started by discussing this. This is just for your reference because I discovered that I didn't have this written in the slides. Yeah. Yeah, go ahead. Will you say this again? After 0405. Oh, here, you want to access this one, right? Yeah, that's a good question. So how would I access this one? If you want, right? So first of all, do you find the use case that you need this one under the following example we have? This one doesn't have a readable value. So assume I want to get this, right? And this is something that is very important to know. When you define, and forget about pointers, and this is a very important question. So, but I'll start earlier with that. So I actually thank you for the question. Please give me your name after the lecture. So your friend here is asking, you keep telling us that assume basically this integer of arrays, I access this one, if I add 1, I go to A1. But what if I want to access something in between? How would I do this, right? This has so many aspects. One of them is called memory alignment issues. Assume you forget about pointers completely. You just define an integer variable called x. Once you do this, it blocks 4 bytes to you in the memory. To make it easy to the software, the hardware abstracts the 4 bytes as one entity to you. We see here in hardware, these are actually 4 different bytes. But the software sees them as completely one entity, which we call x in our variable, right? This has the advantage of making it very easy that you read the 4 bytes at once together. But it has the disadvantage of you don't have the fine-grained control of taking 1 byte out of this. But what if I want to do so? You need to do an extra step. Read the 4 bytes, and then, for example, you guys know AND OR operations, so you can mask some of the bytes, and we will see some of these things later. Assume A1, you said I want to access 05, which is the second byte of A1. Assume A1 holds this value. These are 4 bytes, so this is 1 byte, another byte, and then let's say this, and then this. I'm writing this in hexadecimal, right? This is 1 byte, 1 byte, 1 byte, right? Assume these are the values, but it doesn't matter. This is another example, good? So this is the value that you want to read, which is the first byte, right, of A1. How would I do this? Read A1 as a whole, do AND with all zeros except this one, right? And this will extract this byte for you. Because if you AND something with zeros, it gives 0. If you AND something with 1, it gives you the same value. This is called masking, right? So it's an extra step if you want to extract a certain byte out of a variable. Okay? Why? Because the normal use case is you don't do this. So usually everything in computer engineering is done to accelerate or to increase the performance of the usual use case, right? So the usual use case is if you have an integer variable, you read it at once. To make it fast, the hardware gives the software the access to the complete 4 bytes, not just byte by byte. because it will be slower if you do it byte by byte, right? I hope this answered your question. Yeah? Okay. Yeah, but I like this kind of question. So I said we already discussed this before. The name of the array is actually a pointer to the first element of the array, and you can use it as a pointer. But the thing that we are going to add now is we all had actually these things before, so it doesn't make sense. The only difference that you need to know is, yes, the name of the array is a pointer, but it's not a variable pointer. You cannot change it. If you define an array called int a5, a itself is a pointer to the first element, but you cannot do math operations on that. And this is intuitive, because if you change a value, now you lose the access to this array, right? A has to keep pointing to the first element. So it's a static pointer, or a constant pointer, not a variable pointer. And this gives us some differences in practice. It's not just like an abstract difference. So AA is a pointer to AA0, AI plus I is pointer to AI. We already know this, but I'll come into this later, but this is not what I want to do now. What is that? Okay, so this is the thing that I want to say. Is because A, assume, I guess I have a slide about this later. Okay, this one. So, I keep telling you that array name is a pointer, right? And you can use it as a pointer. But the thing is, it's a constant pointer, so you cannot change. And this makes a slight difference between normal pointers and the name of the array. Inside a function parameter, like if you pass an array to a function parameter, they are completely equivalent. And the reason is, arrays are passed by default by reference, because it takes the address of the first element, and you can operate on that, right? But outside this, outside input parameters to a function, you cannot do math operations on the array pointer. Why? Because it's a constant array. So here, something like int a3, and you do this, we know you can initialize your array by the 3 values, right? But if you define a pointer, if these two are completely equivalent, then this should be accepted, right? But can we do this? We cannot, because Q is of type pointer, not an array. So the syntax is different, right? So you cannot say, I want to initialize an array by value 135. But this means nothing, right? Q is going to point only to one element, but the array by default holds multiple elements. In fact, the number of elements that you initialize it with. So it can say 135. So the compiler understands this, as we explained before, by saying book or reserve to me 3 entries in the memory, point out to this by A, and the value should be 135. But for this line, the compiler will understand this as declare a pointer to me called Q. This should point to an integer. What is this? Right? I don't know. Like, is this the integer value of the Q? But Q should hold an address, not 3 different values. Is this the value of the location that the pointer should point to? But it should point to a single memory location, not multiple, right? You see the difference? So, and this is a trick that is always played in coding interviews, to see if you understand what are the differences. Okay, people all know that array name is a pointer to the first element, but are there any differences between them? The first difference is the array name is a pointer, but it's a constant pointer, so you cannot do math operations on that. The second thing is a pointer itself cannot hold multiple elements like an array. You cannot initialize it like this, right? Any question? Okay, let's go back. All of this we covered, but these are more examples. Here it says, so far we have been using arrays and pointers to point to array elements. So we have 4 different combinations to do this. Assume I define an array of 10 elements. I define a pointer and I say b equal a, which means b should point to a0, right? For the 4th time today. And then if I want to access ai in the array, now I have 4 different values or different ways of doing this. The normal one, which is the first one we covered, which is saying ai, right? ai is element number I in the array named a. But I can also say this, bi, and this is a very neat thing in C. Once you point an array to the first, once you point a pointer to the first element of array, you can use the syntax of the array to the pointers. You can say bi as if b is actually an array, but it's a pointer, right? What the compiler will do when it sees this thing, it will say, yeah, what you mean is add b plus I. Because effectively, these two are the same thing. You add I to b, right? You want to access entry number I that is far from the current entry that b is pointing to. But also, I can use dereferencing, right? I can say b plus I, this is an address, take its value, which is completely equivalent to this one. Or also I can say a plus I, take this value and then point to this one. One thing I said is you cannot do math operations on a, like the array name. But how would I do a math operation here? It seems like a conflict of what I've said before, right? I told you that a is a pointer, yes, to the first element, but it's a constant pointer that you cannot do math operations on. But now a plus I is a math expression. Can someone try to resolve this thing? Yeah. I'm not changing a. What I meant by not doing math operations on a cannot be in the left side of an assignment, right? Here, b and a are not changing. You are just calculating another value that is b plus I, but if you bring b after this, it will remain the same thing. You didn't increase b with I, right? You just calculated an expression that is b plus I. If you say x plus y equals z, z equal x plus y, x doesn't change, y doesn't change, z changes, right? The same thing here, b plus I doesn't change, b doesn't change, a doesn't change, I doesn't change. But you just calculate a summation of both. Good? Any question? You will explore these 4 different things in lab, so if you have any question, let me know. Good. So these are examples, we already covered these. Here, the first one is the one that we had in quiz 2, reading 20 elements, and then assign these elements to an array, right? This is the normal thing. But I can do this using pointers, right? And I can use the same math logic to pointers. So I say b equal a, the first element, keep increasing b, until you reach the 20 elements, and then now you're going to print the value of b. If you do scanf, you can read from the user and put it into the memory location that b is pointing to. So these two loops are exactly the same thing. One is using pointers, the other one is just using the array syntax. Does this make sense? Already discussed. This is also already discussed. Yeah, so another topic is arrays. So if you think of how is the flows going in, we started with very basic things, types, loops, if conditions, the very basic thing of any programming language. We then went into arrays and functions, right? Both work together. And then we jump into arrays of characters, which are strings, which still arrays, but have a specific feature in C, which you can deal with them as one entity, as a string, right? And then we covered pointers. We have seen how pointers interact with arrays, with functions. Now it's the logical thing to cover how pointers interact with strings, which are arrays of characters, right? So the basic rule is they are exactly the same thing as normal array. Like strings are arrays of characters, so they are still arrays at the end. and then you can operate on them. But there are some slight differences because of the nature of the array of character, which is just one entity. Right? So the examples here are like you're defining a normal array of characters. You do a scanf. This is one of the differences between a normal array and the string array or array of characters, is you can read the whole entity as once. Why? Because I'm using here the string specifier. So what is going to happen in this line is read 20 characters from the screen, input it into the array, right? And then finish this by the null character. Oh, by the way, this cannot be 20 elements. They have to be 19, right? Because you have to reserve one memory location to the null character. Right? So if I assign this string hello world, and then I define another pointer of type character, and then if I do the same thing as I do here, I would have a big problem. Why? Because pointer of a type character is going to point to a single variable of type character, but it cannot point to multiple memory locations. This is exactly the same thing as we have seen in normal arrays by saying you cannot say int pointer b equal 1, 2, 3. You cannot initialize a pointer as if it's an array. Why? Because it points to a single memory location, not multiples, not like the array. And because string is nothing other than a normal array, so again you cannot do the same thing. The main reason is, by defining a pointer, it should point to a single memory location, not multiples, not like an array, right? Good. So here, what you would do is, okay, this is character pointer called s, and then you initialize s as John. What happens here is, because arrays of characters can be defined on the fly, you can say this, but the problem is you cannot change it. It's not, this is going to be in the read-only memory. These two things are not completely equivalent. So the correct thing to do is, if you want to define a string, first of all, define it as a normal array of characters, and then use pointers to point to it, right? So we started 2 minutes late, so I have to. So let's take one example to see what's going on. So character s John, this is the example we had from previous slide, and then you cannot say now dereference s and change j to b. So last time we started discussing how to define arrays of pointers. Good? And the thing is, you need to think of arrays of pointers. So until the end of the last lecture, we learned about pointers as just single variables, right? We had dereferencing. Pointers are pointing to our memory locations, which can be an array or any variable. All these concepts, good? Arrays of pointers adds only one slight step towards that, which is I can combine multiple pointers in one array. But the thing that got multiple people confused, and they asked me after the lecture, is if you access an element in an array like bb0, and this is an array of pointers, this now has the array index thing, which is 0. But people don't realize that bb0 is just an array. It's just a pointer. So you can call this pointer 1 equal bb0, and then you use pointer 1, right? And you have all the pointer arithmetic on pointer 1. But you can do the same thing in bb0. So bb0 is nothing other than a pointer. So the thing here is we are defining an array of pointers, which we call bb. It has 3 elements, which each of them has to be a pointer, pointing to integers. And then later what we do is we define 3 other arrays, normal arrays, arrays of integers. And then we make these pointers each one of them point to one of the arrays. So bb0 is going to point to array A. This we have done before, but not with the array indices, not with the array syntax, right? We said before int pointer btr, and then btr equal A, right? We had this before. The only difference here is bb0, it happened to be an element in an array, and it's a pointer. Good. So you can say BB0 equal A. What happens when you do this is BB0 is going to point to the first element in array A. Is there anyone still confused? Good. We do the same thing for BB1, BB2. By doing that, now you have the ability to have arrays of pointers, and each one is pointing to a different array. One important thing you need to understand of what is happening behind the scene is this are all contiguous in memory. Why they are contiguous in memory? Yeah? Because this is an array, and arrays are allocated contiguously in memory. Good? But the thing is, this array and any of these arrays are not contiguous in memory. This can be in any address, starting from address 0. This can be at address 0x55f something. Completely like 1 gigabyte away from this address. Why? Because these get defined separately, and the only thing is we link them using pointer arrays, but they are not contiguous in memory. Right? So one difference, a question that I have been asked yesterday is, what is the difference between this and defining a 2D array? Right? This is not a 2D array. Later you will learn in data structure courses that this is called a hash function. You do hashing by saying you define certain things. Usually you put the key here, and each key is going to point to certain data, right? So this is a usage, like the clear use case of such a structure. Is there any question? Okay. So last time we learned 4 different ways to point to an array element, right? Using A, which is the array name, and then the index A0. Or if B is a pointer that is pointing to A, you can say also B0. These are 2 different ways. But also we can do, does anyone have like third alternative? If P is a pointer that is pointing to the beginning of the address of the array, you can do pointer arithmetic. If you want to access element I, then you can say B plus I, right? Which will be the address of element I, and then you do dereferencing, right? And you can do the same thing with the array name A. So here, what we are saying here is that these 3 are completely the same thing, pointing to 2. How this is possible? A1 is very clear. A1 is the first element in the array, which is 2. This one may be the one that is not clear. But if you think in your mind that BB0 is nothing other than a pointer to A, then it will be clear, because BB0 is pointing to A, and then you can point to an array element using the pointer index, right? So BB01 means BB0 is pointing to the first element of this array, 1 is going to point to the first, like the element afterwards, right? And this is equivalent to this thing. BB0 is a pointer. You do a pointer arithmetic, which is +1. This is an address, and then you do the asterisk for dereferencing to take the value, right? So these 3 things are equivalent. This is not an assignment in C. This is not a C code. This is telling us that these 3 ways of accessing this element are equivalent. Is there any question here? Good? Yeah?
For, let's say we have the feature and everything is the same, but at the end we add plus 2 instead of 1. So would it directly access the third element?
Which is 9, yeah? Because if you do BB2, let's say here, one example, oh, we don't have one for okay, BB2, right? This is what you meant, right?
B3 and the one we have.
B3, this one. So what you do is BB1 is what? BB1 is pointing to, BB0 is pointing to this one, right? Sorry, BB1 is this pointer. BB1 is pointing to 3. If you add 3, then it should point to 6, right? And then you take the value by the asterisk. So this should give you 6, right?
It does not break down all the elements.
No, it doesn't loop through it. It just does a pointer arithmetic to calculate a new address and jump directly to this address. Is there any other question? Okay. So one thing we mentioned about pointers, and the big difference between a pointer, a regular pointer, and a normal array name, which is also a pointer to the first address, is you can initialize an array, but you cannot initialize a pointer by multiple values. Why? Because an integer pointer has to point to an integer variable, but it's just one variable. So you cannot initialize a pointer by having like this kind of array initialization syntax, right? And we covered this in not the last lecture, the lecture before. Good. So now, the normal afterwards step, which is arrays, we have special type of arrays which are strings. Good. So it's exactly the same thing. You can also define a pointer to array of characters, which is string. And then what I'm doing here is defining a character, an array of pointers pointing to character type, right? Then say, S array 0 is pointing to this thing, S array 1 is pointing to this thing, this thing, this thing. Right. So, assume this question is, how do we interchange or swap two strings in an array? How we do this? If I'd like to swap the position of this thing and this thing, can someone mention how we do this easily using pointers? Just the same, like the logic, not the code itself. Yeah. Good. Exactly, but to do this, if you just make this one point to this one, you lost the address of this one, right? So how to do it? You need, what you're saying is correct, but you need one extra step. Yeah, like a temp variable to hold the first pointer. Any swap would require a third variable to basically swap things, right? So what you'd like to do is, by doing the swapping, you define the temp variable, which we call here t. It takes the value of S1, and then you exchange S1 and S2, and then you put the value back in S2, right? Yeah.
Is there any clever way that you can commit using a third variable?
If you can, there is. Think about it. For a bonus mark, let me know next lecture. Okay? Yeah. Why there are 2 stars? That's a good question. And this is almost the most advanced topic in pointers, which we are visiting right now. Why we have 2 stars here? Good? Yeah. It's a pointer to a pointer, which we call double pointer. Okay? So I told you before, let's take the story from the beginning. You have a normal variable, which is int. You have a pointer that can point to this variable, right? Which holds an address to this int. Good? But at the end, a pointer is nothing other than a normal variable as well. So it's stored in memory, right? That means you can take the same thought further and say, I can have a pointer that is pointing to this pointer. And even you can say, I can have a pointer that is pointing to another pointer, etc., right? And this is the concept behind what we call linked lists. This is also another data structure that we'll cover later, is you have links. You guys heard about blockchain? This is like another fuzzy new concept. It's a very similar thing. You have one block of data, and then the way you validate this data is you would like to also connect it with the chain. This is what we call blockchain. So think of linked lists is the same concept. You have a block of data, block of data, block of data, block of data. They are distributed in memory. They are not contiguous like an array. But the way they are linked is each block has data and a pointer to the next element. So once you have one element, once you can access one element in such linked list, you are able to traverse the linked list using the pointers, because you have a pointer that is pointing to another pointer, pointing to another pointer, etc., etc. Right? Just put this in mind. We'll visit this later. Good? Okay, so this is how things work. Now, what does the name of a pointer array represent? And this also related to his question. Previously, we learned that the name of the array is a pointer to the first element, right? But what does a name of the array of a pointer represent? The same thing. It's a pointer to the first element of the array. But it just happened to be a pointer as well, right? So you can say BB is actually the address of BB0. BB0 is a variable, has a value. It happened to be a pointer, but it can be anything. So the concept still applies, right? So BB is a pointer to a pointer, or what we call double pointer. And this is why in this function, we had this double asterisk things. Because you are passing a pointer to a pointer, right? Is there any question? Okay. So a double pointer is a pointer to a pointer. And then if you define, as I said, if you define a variable int a equal 100, and then you define a pointer to this variable, you take the address, which means b is pointing to here. But also you can define a pointer to a pointer using this double asterisk thing to make this pointer point to this one. All right? Yeah.
Is there ever a point where like the pointer to like it gets confused in its own mess where it can't actually handle the amount of pointers that it needs to go through?
That's a good question. So maybe I'll ask the question in a different way. Does that mean if I want to make a pointer to this pointer, I need int asterisk asterisk asterisk, 3 asterisks, and then 4 asterisks, and like, right? No, right? Why this is the case? Because what really matters is what you are pointing to. Assume here I have a fourth one that I call BBB, and I want BBB to point here. What matters is what is the type of the variable that you are pointing to. Remember we said for a pointer you have to determine what is the type you are pointing to, right? So if your type is a normal variable, then you just use this asterisk thing to say I'm a pointer to an int. You use double asterisk to say I'm a pointer to an int. Good? Here, you can say I'm a pointer to a pointer. What is this pointer is pointing to? Later it doesn't matter. This pointer has to care about himself, right? But what I'm saying is 2 asterisks are enough in all cases, because what matters is what you point to. What is the chain is about, it doesn't matter, right? Is there any question? Good? It's getting more funny. So if you have questions, let me know. So here, if, again, this is dereferencing. So the value of P equal A, which is 100. The value of BB is what BB is pointing to, which is this B, which is the address of A, which is this thing, right? And then if I do double dereferencing, then what you are doing is, think of this like this. You are doing the value of BB, which is the address. You can replace this with B, which is the value of B, and then at the end it's A. If you do double dereferencing, you go to the original value itself, right? Is there any question? Good. So if we go back to our original example, BB, the name of the array of pointers is a pointer to the first element, and this is originally its value. If you do dereferencing for this name, it gives you the first element. If you do like double asterisk, which is double dereferencing, then it's like you're doing a dereferencing for the first element, which gives you A0, right? This is exactly the same previous slide, but it happened to be one of the pointers is just an array element, right? So combining arrays with pointers to arrays seems complex, so you have to try it yourself. And like, I also post some exercises, I forgot to say this. So I don't know if some of you visit already the sample questions or sample practice questions that I post in Avenue. And after some time, I also post their solutions. This is also another way to practice things, because sometimes the lab is far behind the lecture, especially after the reading week. For example, we are starting lab 3 after the reading week, but we already covered pointers and we'll move to another topic. So tomorrow in the tutorial, the TA will cover arrays and functions, but also he will cover pointers. Good? So if you feel you need to practice before you forget the concept, maybe it's a better idea to go to the tutorial. we discussed allocating memory last time using dynamic memory allocation. What if I would like to dynamically allocate 2D array? Something of that sort, similar to the example we covered, is you have an array of pointers, each one of them is pointing to another memory location. And I can access this using BBIJ, similar to the example we had. Good. How I can do this? Someone can imagine what would be the logic for a bonus mark? This also was intended to be a quiz, but I just went back. So if someone can think of how I can dynamically allocate a 2D array using such concept for a bonus mark. Yeah. Would you say this? Yeah, yes, for sure you use the malloc function, but how? What is the logic? This is M, and each one of these has to point to an array of n elements. And then you will allocate the whole chunk at once, m by n. So think in this a little bit. This is what I am asking for, basically. How you would allocate this whole chunk of memory, including this and all of that. Am I going to allocate this as whole chunk, m by n? But these are not the same size. This is different than this, right? This is the double element, but these are pointers, right? Good. That's the right way. So please give me your name afterwards. Yeah. Exactly. This is what he was saying, but in different language. So the thing is, for each element of this array, you have to do a for loop and do a malloc, right? Because for each element in the entry, you want to allocate n chunks in memory, and each one of them is double, right? So you have to do a for loop through this array, then each time you do a malloc. Good. So you read m and n from the user, and then mni, and then this is the float of the array, which is this one. So I can write it like this, which is a pointer to the first element, or I can write it as an array structure. But why I didn't write it as an array structure? Because I don't know the size of the array, right? And this is the neat thing about dynamically allocating memory. You just need a pointer, and then later you allocate whatever size you'd like to do. Good. So let's see. First of all, I'd like to allocate the first array, which is the array of pointers. This one has a size of m. And I know that each element is a pointer to a float. So the way I do this, from last lecture, you allocate m multiplied by the size of one entry, which is the size of a float pointer. Yeah. Good. Then we allocated this thing. Now, it's time to allocate the remaining ones. But as he said, you need a loop to loop through these things and then start allocating it. Because the thing is, you need the malloc. You remember the malloc returns a void pointer to the first address. You want the allocation of this memory location to return to you the pointer of this address and place it in the first entry of that array. And here is you create the link between this array and these ones. If you just allocate it anywhere in memory and you don't return the address to this memory location, such connection will not exist, right? Malloc returns to you only one thing, which is a void pointer to the first segment of the allocated memory. You need to place this in the pointer array to create such a structure. Good? So you do a for loop, and then you take the result of the malloc, which is each one of them is size n, and you put it in BBI. So by this line creates this connection after creating the n elements. What was your question?
For the allocation of this, would you need to run the for loop, or would you just deallocate it for the head?
Good. You have to first, and we will come into this. So I don't know if you were the one who asked this question yesterday or someone else. But someone asked me, do I have to, like I said, you have to free memory for yourself, right? But someone asked me, if malloc didn't succeed, what will happen? Does it free the memory for me, or I have to see what was allocated and free it? Now, because you do each of these malloc things separately, I can encounter the case, and focus on this because this is important. I can encounter the case that the compiler is executing my code. I allocated the first array, good. I go through the loop, allocated this, and the third one, I found I don't have enough memory. What would happen? You created this and these two, but the remaining ones cannot be created. What should I do in this case? The third malloc, because it didn't succeed, it will free itself. But these two are already allocated. This array is already allocated, right? So you have to write your logic to say, if everything didn't succeed, then you have to free everything that has been allocated. Right? This makes sense? So another way of doing things is, instead of doing this loop with malloc for each entry, you can, in reality, allocate all these things as one chunk, and then make each pointer of this is pointing to like the n size thing. So instead of allocating different n segments, you can create one total m by n segment, but then each of these pointers has to point to 0, n, 2n, 3n, 4n, right? So if you imagine the memory is just contiguous byte addressable space. You can either allocate these things separately, or you can allocate them at once, and then you point to them different, right? So this is another way of doing things. You just have m by n entries, and now you make the first pointer is pointing to 0, the second pointer has to point to n, the third pointer is to 2n, etc., etc., right? What is good about this thing? Someone else? It's a bonus mark. Yeah? Would you please raise your voice? Would you say this again? I don't hear you. Okay, so say it again. It uses few CPU cycles. No, that's not true, because it does exactly the same operation. It allocates the same number of memory locations, right? Yes, okay, that's something important to discuss. Good. Maybe it's not the topic of this course, but let's go through it briefly, right? What he is saying is, I'm doing this as one step. Oh, this is working for me, that's great. So I'm doing this as one step. On the previous slide, I was doing each one at each iteration. If you look into the two amounts of work, the only difference is what? The only difference is that logic checking at the for loop, which is minimum. It's almost negligible. No one takes into account the condition, because it's just one cycle or two cycles, very iteration. So absolutely you are correct, but from a practical point of view, it doesn't really matter. Right? Yeah. And what is the benefit of that? Yeah, that's one. Yes, that's absolutely one thing. Actually, this what I didn't have this in mind, but that's correct. These things are contiguous in memory. That means you can access them faster. Good. But another thing that is related to what we just discussed right now. Yes. That's true, but it's even further than this. Yeah. You don't need to free them, right? Because it's just a single malloc operation. I told you that in malloc, if the allocation didn't succeed, it just free itself. Previously, because you had separate, because here you had separate malloc lines, each one of them is completely independent, right? But here, in this case, you have only one malloc operation for everything. So if there is no enough space in memory for everything, frees itself. You don't need to care, right? But one disadvantage of this thing, and this is like for 2 bonus marks. Yeah? Maybe we need to use this mic. Yep. Okay, some exercises are okay. Yeah. No, they take the same time. Okay. 2 bonus marks. What is a disadvantage of this thing compared to allocating every array separately? Yep. The memory is? May not be big enough, but you still need, you're in the right direction by the way, but you still need the same amount of memory here. No, but the program is asking you to allocate all of that. Yeah? Here? Yeah, it's here. Any pointer can access everything. That's correct. But is that not correct here? It starts not working, okay. Is that not correct here? That's correct. Yeah, but this is not the reason that I had in mind. But yeah, these two bonus marks. But also, again, it's related to the same reason that you said. Yes. No, but I'm allocating the exact size of memory I'm allocating here and here, right? So, okay, I'll just give a hint, and then it will be only 1 bonus mark. As he said, this is contiguous. This is not contiguous. Yeah? But that's an advantage, right? Not a disadvantage. Yeah, what I was saying is, what is the disadvantage of the second one? Yeah. But that was related to the previous question, so also please give me your name afterwards. This is another advantage of this one. Yeah. Exactly. So here is the thing. I'm allocating the same amount of memory. But in this case, this has to be contiguous. Think of your memory as one big 4 gigabytes, your DRAM, right? Things are running on DRAM like the operating system, other applications are taking different places in memory. It's most probably you don't have 1 gigabyte contiguous in memory free, but you can have different chunks that can add up as 1 gigabyte, right? In this case, if you don't have, assume this size is 1 gigabyte, if you don't have a contiguous 1 gigabyte in memory, this is going to fail. But if you have 1 gigabyte of memory that is not contiguous, like 500 kilobytes here, 500 kilobytes here, and then they add up as 1 gigabyte, as given it's enough to allocate for one array, this will work, right? Why? Because this and this doesn't have to be contiguous, right? This is called, can someone know the name of this thing? Did you hear about this before? It's an important terminology used in both hardware and software. It's called memory fragmentation, right? So this is a good thing to know, right? Memory fragmentation means you can have enough memory space, but it's not contiguous. So if you need the contiguous one, this doesn't help you, right? Okay. For those who took bonus marks, please give me your name afterwards, because people, I don't know why they lose their bonus marks. They answer questions and they don't come to me afterwards. Okay. Great. So how to do this? This is really very easy, because you just allocate the size of this array, then you allocate the whole chunk using only one line of code. But what it remains, you need a loop to make each element here point to the correct place. How to find the correct place? It's time over. Okay, why you guys talk? Because I used that you talk at like 11:20. And this is how I know that the lecture is over. We still have 5 minutes. Okay. So how to know the right place to point to by each pointer is by doing this arithmetic thing. You have a variable that is q. What is q? Q is a void pointer, or now it's a pointer to a float, which takes the first element. And later you have to increase this by I multiplied by n, because you need to jump n steps, right? The first one has to point to 0, the second one has to point to n, 2n, 3n, 4n, right? So you create a loop, and then this arithmetic is giving you the correct address. Is there any question here? Again, what we are doing, we are trying to allocate a 2D array using different ways, right? Okay. If we take this concept further, why I don't make this array also on the same contiguous place as the remaining ones? This is just a normal array. So what you can do is just allocate everything together, right? You don't need now to do 2 mallocs. For the first example, we had how many malloc instructions? We had 1 and then m ones. So we had m plus 1, right? In the second one, we only had 2. Right? In the third one, you only need 1. But what would be the size of this malloc that takes everything together? What would be the input to this malloc function? You need m by n and then this thing, right? The only problem with this is now this is no longer an array of pointers pointing to arrays, right? This is considered just one chunk, and each one of them is just a separate element. Unless you define another pointer that is pointing here, consider this as an array, right? So how to access these elements? We have 4 different ways. We just lost one way, you can use the other ways, which is doing dereferencing using pointer arithmetic. So to access element, which one? Like to go to element j in array n, what you can do, I guess this is array I, you can say I multiplied by n to jump to array number I, and then plus j to access j element in this array, right? This is equivalent to the previous example of bij, right? You can try this example at home because it gives you an understanding of pointers, arrays, and how things work. Good. So I told you one thing is, because in the first example, we allocate each array of the M1s separately. If one of them failed, you have to free whatever has been allocated before, right? So what you do here is, this is like almost a complete solution, using also the checking whether the memory is allocated or not. So what we do, we define an error variable, assign it to 0, and then here we are using calloc, but you can use malloc, it doesn't really matter. And then I'm doing if condition here. So what does this if condition do? I told you previously, if malloc or calloc failed to allocate, it returns a null pointer. And if null is completely equivalent to f0, right? So this is how to check whether malloc or calloc succeeded or not. If they return null, that means they failed. And then you say printf not enough memory. You already failed. Good? And this is for the first array, which is the array of pointers. And then afterwards, you do a loop. You try to allocate each array separately. And you do the same check. If it fails, what would happen? First of all, you have to break, because there is no need to try to allocate more. You already failed to allocate. But also, you need to make an error, you need to make a flag that I failed at one step to allocate required memory. Why this is needed? Because once you exit your for loop, if you succeeded to allocate everything, then the error would remain 0. And in this case, great, you succeeded. But if error has happened to be 1 at any loop, then that means you failed. If I failed, I don't have enough memory, but what do I need to do in this case? You need to free everything that you already allocated, right? How would I know what I have been already allocated? This will... Okay, so last time was our second lecture in pointers, and we discussed more advanced topics in pointer other than just defining them, like doing some arithmetic operations in pointers. and how to deal with them in functions, etc. Today we are going to continue this. We will finish the last lecture first with this topic, which is dynamic memory allocation, one of the most important applications of using pointers in C especially. Did the sound like too loud? It's like, is there a noise? Are you okay with that? In the back? Good? Okay, so dynamic memory allocation. You remember, so far, the way we allocated space in memory was using what? How did we allocate space in memory? Like big chunks, not just variables. Defining a variable, you already allocate a space in memory, right? But bigger than one variable size, how do we allocate space in memory so far? Yeah, arrays, right? Using arrays. We said arrays are contiguous storage in memory that once you define it, you allocate the full space. We said arrays has one big problem, is that you have to define this size from the beginning, right? So once you define an array, the program or the hardware at the end will reserve for you this storage in memory. Whether you use it or not, it doesn't matter, right? They will be occupied for you. And there are some applications that you don't know this space before, right? You don't know how much memory you will need. You cannot resize arrays, at least in all versions of C. And even in the new versions, they do this indirectly. So it's an inefficient way of defining a dynamic memory. We can call this static memory allocation, because you statically allocate a specific say number of entries or size of storage in the memory. But another limitation for arrays, or if you can think of arrays as a storage in memory, is all the variables or all the things that you are going to store in this memory has to be what? What is this condition of arrays? Same type. You cannot store int, character string, Boolean variables, different type of things on the same memory space. So think of this, think of arrays from this perspective. You allocate a specific storage in memory. It has to be fixed. And at the same time, you cannot use this area in memory or this contiguous storage except for the same type you defined your array, right? These are two big limitations of arrays. How to get across this? How to define a dynamic memory space for you and to store in it whatever you'd like to do, because memory is memory, it just stores zeros and bits. It shouldn't matter what type it is, right? How to do this? We do this in C and in most programming languages using what we call dynamic memory allocation through pointers, right? So there are multiple functions of doing this, but this is basically why dynamic memory allocation is important, and this is one of the biggest applications in pointers in C. Before going into this topic, this slide is discussing what we covered before. Is you have what we call automatic storage duration for your variables and even arrays, or memory locations in general. We said once, if you have a local variable, for example, inside a function, it's a kind of a review to refresh your mind. If you have a local variable inside a function, what is the duration that this variable will stay in memory? What is the point that is going to be defined or allocated in memory when you enter this function, right? When it's going to be deallocated from memory when you exit the function. So if it's a local variable, the duration that this variable will stay in memory is within the block you defined it, whether it's a function or a for loop or if condition or whatever, right? On the other hand, if you want something to stay in memory for the complete duration of the application, you have to define it as what? Static, right? So if you define a variable as static, it gets defined, it gets allocated in memory at the beginning of the application, and it gets deallocated at the end of the application or the program, no matter whether you are using it or not. But defining it as a static doesn't mean you can use it anywhere in the program. So static and global has two completely different meanings. Static is with the duration of like how much time or what is the duration that this variable will stay in memory. It doesn't imply anything about its usage in the program. if you have a local variable, it can be static, so it resides in memory, but you cannot use it outside the block you defined it. And we had an example of that, right? This is a static variable. On the other hand, if you want a variable to use everywhere in your program, then maybe you need to define it as global variable, right? So this is what we discussed, maybe like in a brief or nutshell, about memory allocation and the time or the duration that a variable stays in memory, right? As you can see, this is like very, very limited thing. So basically based on the type, you have limited rules. You have to obey these rules, good? If you want to get across this, you need to use dynamic memory allocation, good? So you can do dynamic memory allocation in C using two main functions, malloc and we call it calloc. So malloc is the mostly used one, and this is referring to memory allocation, malloc, right? And calloc is very similar, but the difference is basically it refers to contiguous allocation, and as we will see, it has little differences between malloc and calloc. Reallocation or realloc is if you already define the space and you want to change its size, for example, right? So what does these functions do? They reserve for you also a contiguous portion in memory, and they return to you a pointer to the start address of this memory location. Somehow very similar to how array works, right? Once you define an array, the array name can be used as the start address of the array. So if you think of an array as a contiguous memory, then the start address is the address for the first element, very similar to here, right? But using malloc, let's focus on malloc and everything else is similar. If you use malloc, first of all, you can resize the memory that you defined. The second thing is you are not tied to a specific type. You just define a memory space for you. You reserve it if it exists. And then it returns a pointer to the first address. You can store there whatever you'd like to do. Good? So it's called dynamic memory allocation. So one last thing is, and this is the cost of having a fine-grained control in C. You define your memory yourself. So you have to take care of, you release this memory once you are done with it. Otherwise, your program will run out of memory, right? And one of the biggest mistakes, like this is something that is very common in C, especially for someone who is not familiar with C and is familiar with other languages. In C, you handle the memory yourself, right? So you allocate a chunk of memory, you deal with it, and then at the end you have to free it. People forget to free the memory. And then they exit the program, like not exit the program, like they exit the function. For example, they're using this memory and go to another function. They try to do another malloc or do another array definition or something that uses memory, but the program crashes. The reason is you don't have enough space in memory. Why? Because you allocated big chunk, you used it, but you forgot to free it. So you have to use the free function once you are done with your memory allocation. So the steps to do this is you start with allocating a memory that you would like to use. Try to be constraining for yourself. You can define whatever you'd like to do, but use only the memory that you need. You perform your operations, and once you are done, you free. Good? Okay, so let's see some examples of how to do this. But before going to malloc, I told you that malloc is reserving to you a certain storage in memory or a certain portion in memory and returns a pointer to the first address. But what we covered so far is a pointer has to be to a specific type, right? We discovered like int pointer, character pointer, double pointer. So a pointer is an address that is pointing to another variable, and this variable has a specific type, right? But now, I told you that the second limitation of an array is you have all the memory that is allocated to an array has to be of the same type. This does not exist in dynamic memory allocation. But how to do this? The way they do this is the returned pointer from the function, which is malloc, is of type void. It basically is not constraining you with any type. So we have in C what we call a pointer to a void. So it's not pointing to a specific type so far. You can later reallocate it to a certain type. And this is the good thing. This is the trick, right? But because this is a void pointer, it's not pointing to a specific type, we cannot do math operations on in this pointer, right? Why we cannot do that? Because if you remember from Monday's lecture, to do math operation on pointers, you use the size of the data type that the pointer is pointing to in your math calculation. So we had an example of if you have a pointer to an integer and then let's say to an array of integers, you have, like the pointer is pointing to A1. If you want to go to A2, you just say B plus 1, where B is the pointer. Why does this work? Because the compiler is going to take the 1, multiply this by the size of the integer, which is 4 bytes, and then jump to the second element, right? So the math, if you look into the early slides of this lecture, there is a math equation where the size of the type is included in the pointer arithmetic, right? But if you have a void pointer, you don't have a specific type, and in this case, you cannot use this equation, right? You don't know what is the size of the memory that you are pointing to. Is it 4 bytes because it's an integer? Is it a character, so it's just 1 byte, right? This is why you cannot do a math operation on a void pointer, right? Later, if you reallocate a pointer of int and then point to the same address, then you can use the other pointer, right? And for the same reason, you cannot do dereferencing with that pointer because it has no value. It's not pointing to anywhere, right? It's pointing to a specific address, but not of a specific type, right? So this is the usage of malloc. This is the prototype. It returns a void pointer, and it takes an n. Size t is inherently an integer value, but a specific type in C. I'm going to explain this right now, but this is referring to how much memory you want to allocate for yourself, right? So what happens is it allocates consecutive bytes of memory. It returns a pointer which is void 1 that is pointing to the first type. What if I don't have enough space in memory? Because I keep telling you that this is dynamic memory allocation. You can do this on the fly. But assume I'm trying to allocate 4 gigabytes and I don't have that much space in memory right now. What will happen is malloc is going to return to you a null pointer. Good. Later in your program, you have to use this null pointer as an indication that your memory is not allocated. Otherwise, if you don't take this into account and you try to use the memory, you will have segmentation fault. You are referring to a memory location that does not exist. Good? So what you need to do is, if malloc is returning a null pointer, you have to do a check in your program before using the memory that you allocated for yourself. Good? We'll have some examples now. Before going some examples in malloc is exactly the same thing except that it takes 2 things. Because the way malloc is allocating memory, malloc is a contiguous place in memory that is not of any structure, right? Malloc on the other hand, it allocates a memory space as if it's for an array, right? This array has m objects and each of these m objects has n bytes. So, as if you are defining an array, I can use my pen here. And then you have in this array m objects. Each of them has the width of n. This is how to interpret calloc, right? On the other hand, malloc is just 1 byte width. This is why you don't need the other variable here. And then it has here, in order to make it the same syntax, let's call this m, and this has m objects, right? So for malloc, you have m objects, each one of them, or m entries, each one of them is just 1 byte by default. So it's a contiguous place in memory. But calloc, the way it defines it, you have m objects, but also you have another number here, which is n, which is telling you what is the width of each entry here. Good? So think of this as if you have m integer objects, and each one of them is 4 bytes, right? Because integers are 4 bytes. Right? So there are very little differences between malloc and calloc. One of the differences is calloc because it somehow inherently tries to simulate array reservation in memory. It do initialize all the memory locations for you, right? So if you allocate a memory space using malloc, it does not get initialized. Whatever garbage in the memory, if you read it without writing into it, you are going to read it. But memory allocation that is done using calloc, any memory address within this portion is initialized to 0. This is good because it does the initialization for you, but also it has a disadvantage that calloc runs slower than malloc because memory allocation takes time. One of the things that consume time in C is memory allocation. So if you do memory allocation using calloc, you have to take into account that if it's a large chunk of memory, as if you are doing writes to all these memory locations. So it takes some time to get it allocated. So if you don't need the initialization, actually it's not important to use calloc. And most of the big programs are actually using malloc, not calloc. Okay? But other than this, there is no big difference between both.
If you can't make a request, do the ones like that agree, are they still initialized? So do you still have to free it?
Yeah, for both you have to free it.
Like what if it can't make the request? Does it still fill up some memory? And then it realizes it can't make the request?
You cannot make a request means you cannot allocate this. So I don't get your question.
So for example, there's like a certain amount of memory.
Yeah.
And when does it realize it can't make a request? At the end or before it starts?
I see what you mean. That's a good question. So your question is while I'm doing the allocation, when I realize that I don't have enough space, is that when before I start or I keep allocating until I hit something, right?
Does it initialize exclusively?
Yeah, this depends on the hardware because this function is using some hardware support. Some memory structures, which are the common for high performance ones, keep a list of how much empty storage you have in your memory right now, such that if malloc or calloc are used, and by the way, both are dealing with this problem the same way. So there is no difference between them. Initialization have no effect here, right? Some of the hardware will tell you at the beginning, you already have so much space. So you compare with this space, and then if it's larger, then you know from the beginning you don't have an issue, right? And then you can just allocate. But even in this case, you are not sure that you are running alone because you can have hundreds of programs running. All of them are trying to do malloc or calloc at the same time, right? So even with this support, you still can have the case that you start allocating and you hit a point that you don't have space and then you free anything. We'll have one example right now that you need to handle freeing the space yourself in some cases. But in most cases, what will happen is either malloc or calloc, if they already allocated a space, and then reach a point that there is no much space, and this space that is allocated is less than the size that you asked for, they by default free everything, and then give you a null pointer. So they do the free for you, right? Is there any other question? Good. So as I said, to deallocate the memory, use the free. Free is taking an input, a void pointer. What is this pointer? What is the input parameter to this free? Malloc had no input parameter. Why free has an input parameter? Yeah. Yeah, which is the same pointer that is malloc returned, right? So you have to give free the start address that the memory has to start free, right? So this pointer is like the address of the house or the address of everything that you allocated for yourself. Why you need to free, right? And then it deallocates the memory starting from this. And if you try to free something that you didn't allocate using malloc or calloc, it will give you an error, right? And then if free didn't do the free for you, it will return a null pointer. So again, you have to, if you want, you can double check whether the free operation is done successfully or not. Right? Okay. As I said, you have to free the memory that you no longer need, otherwise your program will run out of memory, right? And it will be inefficient. The allocation, this is not required from you, but this is for your information. Assume I already allocated something dynamically using malloc. Allocated, I don't know, like 1 megabyte. Later, I found that my program needs more memory. And I need this memory also to be the same chunk as the 1 megabyte, but I want to increase 1 megabyte to be 2 megabytes. Then you can use reallocation, realloc. The way realloc works internally is it's not necessarily going to reserve the 1 megabyte that is directly sequential to the first megabyte, because you are not sure this will be free in the memory at this time, right? So if it's free, it's going to be allocated, but if not, then it's going to be allocated somewhere else and then point to this place. So as if virtually, they are one chunk, but physically in hardware, they don't need to be contiguous, right? So the problem with reallocation is you are not sure that the new space is going to be contiguous or the same block that like the malloc did. By the way, why I care whether this is contiguous space in memory or not? I already mentioned this before, but can someone say a hint for a bonus mark? I keep saying malloc or calloc or array gives you a contiguous area in memory, like storage in memory. Why this is important? Some new face from the back. Why it matters? Yeah.
Because if you want the user to, let's say, input value into an array, and you're going to input, then you can use this, you can use it on calloc.
Even if they are not contiguous in memory, you can still use them as if they are one entity. So there is a difference between whether they are physically contiguous or not, right? So what you are saying is, if they are contiguous in memory, I can use this as an array and then increase the index, for example, right? Is that what you are saying, right? So what I'm saying is, there are some data structures, we didn't cover this yet, but even if you get allocated entries that are not contiguous in memory, you can still use this index pointing to it. But it's not related to programming or usability of programming. Yeah? Specify the data type. No, here in dynamic memory allocation, you don't have to specify a data type. Some other new case? Yeah? Yes. Why this is the case? Why they are faster to access? They are beside each other and then they can get allocated to the cache near the processor faster, right? So I told you before that the way your laptop is structured is you have off-chip memory, which was what we call DRAM, and then you have on-chip. On-chip means it's close to the processor, faster cache, right? And accessing caches are much faster than off-chip memory. Like caches are like 1 to 10 cycles. Off-chip memory is like hundreds to 200 cycles. If something is contiguous in memory and you access it on the off-chip, everything is brought to the cache at once, and then you can use like faster access to it. So caching mechanism in hardware is highly reliant on what we call locality concept, and locality is based on whether this memory space is contiguous or not. So if you are accessing something that is contiguous in memory, it's much faster than something that is not contiguous. Later, you will see this in data structure course. The access time of an array, access time means how much time it takes to access an element in an array. It's called O1, which means it's constant time. Whether you access first element, last element, mid element, doesn't really matter. They take a constant time. In other data structures, which are efficient in other cases, but their access time is not constant time. Why? Because they are not contiguous in memory. Array is contiguous in memory. Good? Is there any question? Okay, so let's use dynamic memory allocation in defining a variable length array. Good? Assume I have a main function, and then I ask a user to input to me the size of the array. It's the first time we do that. And then I read the size of the array using scanf. By the way, I need to check whether this size is positive or not, because if it's less than 0, I cannot allocate an array or any memory location of negative size, right? So this is a check that we do here. It's a sanity check to make sure that the user is not doing something wrong. Right? And then I use malloc here. People are here, I use malloc here to allocate the size of the array that I want. Assume that this is a float array. The way I do this is I multiply n by the size of float. What is that? What I'm doing here? If you have an array of type float and it has 10 elements, and you assume that the float size is 8 bytes, assume this for now. It's machine dependent, but assume it's 8 bytes. That means this array that has 10 elements, how many bytes it needs in memory? 10 multiplied by 8. You need 80 bytes, right? This is exactly what we do here. We have an array of size n, but I know each element or each entry in this array has a size of 8 bytes. This is what size of function is doing. Size of is a function in C that takes as an input multiple things, multiple different things. It's like a magic function. It can take a data type, as you have here, size of float. We used this before, right, to check what is the size of int in our machine. It can take an array, it can take a variable, and it returns to you what is the size or the memory number of memory bytes that are allocated to this type. So for example, size of float, It can be 4 bytes or 8 bytes, right? And then multiply this by the number of entries. This is how much chunk in memory I need to reserve for that array, right? And it's done dynamically. Then malloc, I'm taking its output to a null array, right? Here I'm defining a float pointer, it's null, and then I'm reading the thing here. Why it's float? Because I know for now this is a limited example because the whole chunk is of the same type, float, right? We can say malloc can actually store anything. It's not necessarily all elements are floats, but for now we are using it as floats. And then I'm returning a pointer to a float. Good? Then let's say I want to loop through this array or dynamically allocated memory and then print it back, right? Or read the values and then put it in the array and then print it back. So after reading the size of the array, I ask the user to input the array elements. I do a scan. Now here is a trick. We had this before, right? Last lecture, we said to access an element in an array, there are four different ways. One of them is to use the pointer that is pointing to the first address plus the index of this element. So b plus I is effective too, as if you are saying AI of an array, right? Add this before. Good. And then here I'm printing back all the elements of the array, right? Saying like b of 1 equals this, b of 2 equals this, etc., until I finish n. Is there any question here? Good? Okay. At the end, before I finish my program, I have free b. This is how you do the free. b is the address, the pointer that is returned from the malloc function. You use the same pointer to free the whole chunk of memory. Good? As you can see, free doesn't need a size, right? Malloc takes a size, but free links that you already allocated this portion of memory, b was pointing into it, and then if you pass back b into this memory, it knows already the size. Right? This is why you need to pass exactly the same pointer that you got back from malloc. Any question? Yeah. Yeah, what is this, right? There was a slide that I left for you for reading, and it has this information. It was, I guess, 4 lectures before. It's basically telling you how many digits you print and what is the accuracy for this. Right, so go back to this slide and you'll find the answer. Any other question? Good. So now we have another example. Let's say we want to write a function. Honestly, originally, my original plan was to add this example as a quiz. Right? Because it's a long time since we had a quiz and it's not fun, right? But because pointers took too much time than what I have expected, and because you ask questions, but that's good, I like that. So I'm thinking in a different way of how to handle the missed quiz that we missed so far. But I'm going to explain this example for you. It's not a quiz, right? So if you have any question also in this example, let me know. And think of if now I give you this as a quiz, whether you will be able to handle it or not, right? Right? So think of, because if you don't have any question, that means you either completely lost, which is too bad, or you guys know everything, which means you can't solve this quiz, right? Okay. So what we want to do is we want to write a function that adds 2 n-dimensional vectors. Vector is like a different terminology than an array. There are slight differences because vector is actually a data type in a C library that uses dynamic memory allocation. It's not like an array. It can be a variable size array. But for now, let's say, this is why I don't call this n-dimensional arrays. Because people usually use array word for the fixed size. If you have a dynamically allocated array, it's better to call it vector. This is the language that the programmers are using. Right? So to add 2 n-dimensional vectors, each vector is stored in an n-size array. Then the array names corresponding to the vectors to be added are passed to the function as arguments. So I want to write a function that takes as an input 2 vectors and adds them. Seems pretty easy, right? Except that n now is variable, right? This is the difference between whether you know the static size of the array or not. you have different options, right? I can, on the main or the caller, I can create an array that will store the result and then pass to this function a third parameter, right? As an array that holds the result of the addition. And because arrays are passed by reference by default, then if the called function or the add function is going to modify this array, it's going to reflect in the caller, right? Or now, given we already know dynamically allocated memory, I can write a function that stores the sum in a vector or a place in memory and return a pointer to this vector, right? I told you before you cannot return an array from a function, right? But you can return a pointer from a function, which can be a pointer to an array, and this is the trick, right? So this is our main. We define, we initialize the vectors. You can get the vectors using user input, whatever, but now we have them as initialized. And then you define an integer pointer, you initialize it to null, and then we write our functions like this. Takes vector 1, vector 2, and 4, which is the size of these two arrays. How would I write this function? Right? This is the thing. So one way of writing this, say these are two arrays. I take these by reference, which is by default. I take n, which is the size. I define an n sum of n. Can I do this? You can do this in later C versions, as we said before. You cannot do this in C89. You cannot define an array size of a variable, right? But you can do this in C99, and we said this is not allowed in this course, but let's go forward with that. What I'm saying is this is actually not efficient. Why it's not efficient? Yeah? But you have to create a third array anyway, right? How would I add the two vectors? You are not allowed to change the two vectors, right? You have to create another storage anyway. And its size is equal to the size of the arrays, right? Do I have to take n as an input? Do I need even to define this n thing, which is limiting me? Now, given we know how to dynamically allocate like memory or arrays, I don't need even n. I can get the size of v1 and v2 and use this in my problem, right? So a different way of doing this is assume, but even before this, assume, this was assuming that this was allowed in C, right? Assume that in your X company, you are not allowed to use the later versions of C, like 99 or C++11 or something of that sort. Then you are not allowed to do this. Then this has to be constant, similar to what we covered before. So now, if I define n as a constant, what would be my size? Are you guys lost? So here is the thing. This is allowed in some versions of C. It's not efficient because you need to know n, you need to pass n, and then you use it. But there is also another limitation, which is some versions of C and compilers don't allow this. Don't allow to define an array of size variable. N is variable, right? What if I'm not allowed to do this? How to do it? You have to have the size of the array as a constant. Like let's say capital N or M or any name. That means you need to define it from the beginning. If I'm defining n capital from the beginning, what would be my size? Yeah. 4 if you know 4, but n is variable. You can read n from the user, right? We agree on that. So it has to be large enough to accommodate for the 4 for this example, but in general, it has to be large enough. Basically, the condition is n capital has to be larger than or equal to n small, right? If you don't know n, then the safe side is to allocate n capital as very large number. Right? This makes sense? Is 1,000 enough? Is like 10,000 enough? Is like 1 million elements enough? You never know. But if you allocate it large enough, you lower the probability that it's going to fail. Right? But, yeah. The problem is this is an array. You don't free an array yourself. It's going to be freed when you exit the program, right? So you don't have control on how to free it. Yeah. So if this is a local array within this function, it only gets allocated once you enter the function, deallocated once you go back. You don't have control on that. But you are in the right direction. Like if n is very large, I get allocate this large chunk of memory, like an array of size, like 1,000,000 elements, and I end up having an input of only 4 elements. That means I wasted 1,000,000 minus 4 memory spaces for no reason, right? So this is why it's inefficient. Do you get that? It's inefficient because you have to define something static, you have to be conservative because you don't know what to expect, and you just allocate a very large chunk. Yeah, what's wrong with the small n is it's not allowed. There are 2 things wrong with it. First of all, it's not allowed in all versions of C. Like C89, it's not allowed. For NCC, it's not allowed in C. So the compiler will complain. Right? The other wrong thing, and this is why we needed this, the other wrong thing is also if you do the other thing in allowed versions, it's for sure more efficient than this solution, but you still have to pass in as an input parameter, and right? You still do some extra work that if you have dynamic memory allocation, you don't need. I can write this function completely without passing in, using the information we covered in this lecture, right? But you see why this is inefficient, right? Okay, so how to write it then? Then one way to write this, and by passing in, so as I said, you don't need to pass in because you can get this size from these arrays inside the function. But for now, let's focus on, if I pass in, how to get across the n capital large chunk. If I just have n, I only allocate whatever is needed. How this is different than the n capital thing? malloc, even in all versions of C, allows you to pass a variable number of entries, right? So this is valid in C89, and n doesn't have to be a constant. So you can pass n as a parameter, and then you only allocate whatever you need. In one run of the program, the user may enter n as 4. In another run, it can enter n as 4 million. And in both cases, the memory is allocated on the fly, right? So it's dynamically based on the user use case. And that's why it's efficient solution, right? Is there any question? Yeah. What is the difference between passing then or not passing it? Oh, what is the difference between this one and the first example? So there is no difference, right? Except that this is allowed in all versions of C, right? So I guess maybe the first answer of your first question was confusing, but the first one was a correct solution if it's allowed by the compiler. There are some cases that, but then maybe you guys ask yourself, okay, this is an old version of C, why I'll just use the new version anyway. It's not possible in all cases. In some projects, big projects, like in a specific use case, you have to use a specific version of C because of a certain support. For example, you work in a company that they had a project that was written 10 years ago, right? And then you have to do something with this project because another customer wants to enhance it. Then you are limited to this specific version of the program. You cannot change everything. It takes you like months and money, right? So in some cases, you are tied to a specific version and you have to deal with that version. Okay? Is there any question? Okay. So did you think if I gave you this as a quiz, you'd be able to do it? If not, then I guess maybe you guys need to start studying pointers because it's getting complex each lecture. Right? Okay, so more fun, arrays of pointers. We covered pointers to arrays, how to pass pointers to functions, how to return pointers from functions, dynamic memory allocation. Then pointer, I said this last lecture, at the end it holds some memory address, but at the end it's just a variable, right? You can define a pointer as a variable. So, and it's also stored in a specific place in memory, right? So what prevents you from defining arrays of type pointer, right? Each element would be a pointer. I can do this, right? And this is what we are covering in this lecture. So I can define an array of pointer of size 3. Can we imagine what is going on here? This will be an array that has 3 elements. And what is this telling us is each of these elements is an address to another place in memory, right? It's a pointer. Right? Make sense? Yeah.
So you have 3 arrays?
No, not necessarily arrays. You can have 3 arrays, but you can have just 3 elements here. Right? This is a good question. What do you think? Based on the type we defined here, that means each of these pointers is a pointer to an int, right? So this has to be an int. You cannot have a string or like character or something here. Yeah, it will not work. You have to define this as a size of like a character or something, right? So arrays of pointers is telling you what is also the type that the pointer is pointing to. Right. So here, I don't know if you see from what I'm writing, but I'm initializing an array with 2 elements, 1 and 2. Another element. I guess maybe I should just use this. So here, I'm initializing 3 arrays. This is A, this is B, this is C. Then simply, because all of these are arrays of integers, I can make each pointer of this is pointing to this, as your colleague said, right? If I say BB0 is A, it's going to take the address of A. And then B, the address of B, C, the address of C. Right? So using arrays of pointers as if you are defining array of arrays, right? Because each entry in that array is an address to another array. Right? Does it seem fun? Okay, so if I want to refer to element AJ in array A, let's say A1 here. What you can say is, you know, A is pointed out by BB0, and then you can use another index here, J. This will, like BB01 will be 2, right? And the same thing for these things. So if you say A1, this is completely equivalent to BB01. In the last lecture, we also had this, which is dereferencing. If I say BB0 is a pointer that is pointing here, you can add the index here and do dereferencing, right? This is a pointer math operation. Here, because it's getting complex, please focus with me. What is going on here? BB0 is a pointer, right? It's a pointer to the first element in A. BB0 plus 1 is a math operation on a pointer. So adding a 1 to a pointer of type int is going to add 4 bytes, right? Which means you can use this as your index. And we had an example last lecture. So that means you are here, you increase 1, you go here. Again, this is still a pointer. What does the asterisk do? It does dereferencing, which means it's taking the value that this address is pointing to. So BB0 is here, add 1, go here, take the value, it's 2. Everything of this is the same. Right? Another example here. Good. So this is similar to what we said in last lecture. You cannot initialize a pointer. So you can have a pointer that is pointing to an array, but you cannot initialize a pointer with multiple elements, as if it's an array. So this is a syntax error, exactly similar to the previous lecture, because at the end BB3 is a pointer, and you cannot initialize a pointer like this. So one step further. But first, do you have any question here? Or do you have any question in general? this, right? Okay, so let's take it step by step. A1 is 2, right? BB0 is this one, which is an address now by doing BB0 equal A, is going to be addressed to the first element of A. If you say BB0, replace this in your mind with a pointer to the first element of the array. We said in the last lecture, you can use a pointer to an array using the indices, right? So if you say, like let's say I call BB0 another pointer, I call it pointer, BTR. Can I write BTR1? I can say this, right? Because BTR is a pointer to array A. A is an array, so you can write A1 or BTR1, right? So this is exactly the same thing. The way it works is BB is an array, BB0 is a pointer, BB0 is pointing to this one, X is the first element of the array that BB0 is pointing to. BB01 is not a memory location. Oh, it's a memory location, right? A1 is an element to that array, which is also a memory location. Oh, you mean not a memory address. This is what you mean. Yes, it's a value of this address. So if you use a pointer using the indices of an array, you are doing dereferencing. This is another way in C of doing array dereferencing, right? If you say B0, you are accessing the element of the array that B is pointing to, right? Of 0 or 1 or 2 or 3. Yeah. If you print, this is a good question as well. If you print BB0, it's going to give you the address here, right? Because here we store an address, right? And you can try these things yourself, right? So you try them, it will give you the address of the first element. Yeah. First, I have 2 minutes. Second, these questions are very important ones, so I guess you don't want to miss. Assume you want to miss and you don't care, at least respect your friend who is asking, right? That's a very good question, right? If you are thinking about access time using this way, you are right. You can like accessing this element because this one too can be in anywhere in memory. It's not contiguous to this array. So it's from this sense that's true. But from another sense, access time is one aspect of a data structure. But also the search is another aspect, right? So what I mean by this is to search an array